Hello, my name is Shurat Das, and I welcome the professor and the TA to this presentation on the final project of E554. For us, this is the human 3D pose estimation through the help of transformers. My teammates are Manan Saxena and Sujit Mukherjee. It's been some time after the progress video, so I would like to restate the entire problem. So, human 3D pose estimation is the task of estimating the 3D positions and orientations of human body joints from a given input image, video, or a sequence of images. The goal of this task is to accurately infer the spatial configuration of a human body in 3D space, including the positions and orientations of joints such as head, shoulders, elbow, wrists, knees, and other parts. 3D human pose estimation is an important problem in computer vision and has applications in various fields, including sports analysis, healthcare, robotics, and virtual reality. It is a challenging problem due to factors such as varying human body shapes, like different shapes of different subjects, clothing, lighting occlusions, and camera viewpoints too. So there are several approaches to human 3D pose estimation, including model-based methods that use a pragmatic, a parametric model of the human body and estimate the model parameters from the input data, and model-free methods that directly regress the 3D joint positions from the input image using deep neural networks. So, recent advances in deep learning have led to significant improvements in the accuracy of 3D human pose estimation, and this area of research continues to be an active and important area of study, and that's the main reason behind our choice of the project. So, the entire project is divided into several parts. The first step is to load the data. Uh, for our choice of dataset, we actually asked the professor to provide his own mocap dataset. But the problem was that the paper that we were referring to, the post farmer paper, wasn't actually conferring to the way in which the data was provided in professor's dataset. So we actually then proceeded with using the human 3.6M dataset. So first, data is loaded and put in the transformers. So how does it work? There are specifically two types of transformers used in this model. One of them is the temporal transform, and the second is the spatial transform. So, what are temporal transformers? Temporal transform models are basically designed to process sequences of data such as videos. Uh, they basically use self-attention mechanisms to selectively attend to different parts of the sequence, allowing them to capture long-range dependencies between frames, like grabbing what the entire context of the video is. Uh, Temporal transformers are basically used to process and find out, extract the feature vectors and generate a sequence of 3D joint positions. So by attending to different parts of the sequence, the model can capture the temporal evolution of the person's pose and generate more accurate 3D joint positions. Whereas the spatial transformers are designed to selectively transform different parts of the image on attention mechanisms. So in the context of our project, so what we are doing is basically we are taking the spatial transformer that models different parts of the 2D image and more specifically extracts the relevant features of estimating the 3D positions. Like for example, the model can learn to focus on the person's body parts and ignore the background on other relevant parts of the image. So together they are actually combined to yield a very good estimation of the human pose. So, after the brief overview of the project, I would like to go over through the essentials and the intricacies of the project. So, this is the entire timeline of the project. I know that we have submitted a progress report, but I wanted to go over through it once more. So, after using the H36M dataset, we actually faced with a major complication, and which was of not finding access to a GPU. We know that we had pleaded the professor to help us grant access to a GPU, but it is technically not possible for the professor to grant access to a GPU to every team. So it took us some time, and finally we got access of one GPU. Then we basically trained the original model on the H36M dataset. It was good, uh, it was doing well, but we wanted to add something more from our own knowledge, which was the bone length loss. I would talk about this when we are proceeding through the slides. The major problem that we faced while using and training the model was that we thought that it would be really good if it could train through a lot of epochs and it would provide a very good result. But at the end of the fourth day, it actually stopped because the GPU had crashed due to out of memory error, and we actually had attained only 41 epochs. So this is the entire code flow where we are actually taking the data set, the raw data set of H36M. The problem with the H36M dataset was that it was in a TXT format and the model could not implement the TXT format. So we had to write a script which would convert the TXT format to an H5 format, which would later be processed by the video pose 3D main file and hence yield the 3D pose estimations. This is the code, rather the script, which converts a TXT into an H5 format. It's a very basic code. We had to find out the patterns in the text file and see what we require for the model to train. The most important part of this project was making the model understand how to perceive a human skeletal system, because it has no idea of the human body in prior. So what we had to do is basically we numbered the joints, and by numbering the joints we actually labeled them what means what. For example, 0 means the hip, 1 means the right hip, 6 means the left hip, 14 means the right shoulder, 11 means the left shoulder, and so on. So there are 17 such joints, 0 to 16, and we basically code them such that we map the entire human body skeletal system into the model. Next, we add something on our own that we have already talked about, the bone length loss. Originally, the model was using a loss function known as the MPJP, the mean per joint positional error, which would just compare the 3D estimated poses with the ground truths. But one part left unattended. That is the biological length of the bone. The transformer has no idea about the biological length of the bone, and it would just spit out some prediction about the 3D position without considering the length of the bone, if it changes or not. So if you consider this thing, for example, a human is moving. For example, we are moving, we are walking. It doesn't make sense if the length of the bone changes at every on every action we take. It doesn't happen in real life. So we need to implement that in the code. That's why we introduce the bone length loss, in which what we do is that after every feature extraction, we try to concatenate this loss with the actual MPJP loss, and what it does is basically it takes in the 3D pose estimation, understands calculates the bone length through the Euclidean distance formula and compares it to the actual bone length. So it should not change when you are giving a prediction, no matter how good the prediction is. If it is not realistic, it's of no good, right? So yeah, this is the screenshot of how the GPU stopped after 41 epochs at the end of the 4th day. It was taking about 2.5 hours, 1.5 hours to 2.5 hours for each epoch, because it's a big model. We know it was made by Google and they use TPUs and stuff like that. We used a single GPU and we shouldn't have been so confident about running it to 1,000 epochs. So yeah, we did what was possible for us. So this is the result that we obtained after the final training, like after the code stopped. This was the training loss. This was the evaluation loss. We see a lot of jitter here, and there has been very minor improvement because it was just 41 epochs. It was not enough. And yet the learning rate actually slows down or actually comes down when we reach a global minima, as we have seen in any optimization problem. If this is the curve and we want to reach the global minima, basically the learning rate has to decrease as the iterations proceed, so that we slow down when we are reaching the final position. Thank you again for having a patient hearing to the entire project. It was a very difficult project. We tried to give our best and hope you liked it. Thank you.